Okay, good afternoon, everybody. I hope everyone is safe and doing okay. Today, we're very happy to have Mykhaylo Usatyuk from KITP, and he will tell us about near-extremal black hole evaporation. So please, Misha, take it away.
Great, thank you, Shahar. Today I'll be telling you about some work that's primarily based on these two papers in the bottom. And it's about how near-extremal black holes evaporate. Um, so just to give a kind of very broad outline of the structure of the talk, um, the talk is going to have roughly four phases. In the first part, I'll tell you some basic facts about semi-classical near-extremal black holes, just in the framework of general relativity and quantum field theory. Then I'm going to tell you how we can study quantum black holes. And the main tool here is going to be the gravitational path integral. So I'm going to tell you how the gravitational path integral can be used to study quantum properties of black holes. Then I'm going to tell you how the gravitational path integral informs us about uh, big quantum gravity corrections to various dynamical processes of the black hole. And this is going to be split into two parts. It's going to be on quantum corrections to the evaporation of neutral particles. What I mean by that is the black hole emitting things like photons and gravitons, and also charged particles, say like electrons and positrons. Um, and then finally, I'm going to be able to combine all of these ingredients to tell you kind of the lifetime and the history of a very large charged black hole, how it emits various types of particles, and gets to the endpoint of its evaporation process. Okay, so let's get started with semi-classical black holes. So in general relativity, black holes are characterized by three numbers, right? They're characterized by a mass m, an electric charge q, and an angular momentum j. And if we fix the charge q and the angular momentum j, we can ask for what values of the mass does a solution exist. And in GR, a solution exists anytime the mass is above a minimum quantity. And the minimum quantity is specified by this inequality. So when the mass squared is greater than the spin squared over the mass squared plus charge q squared, the black hole exists. And this inequality is a little bit non-trivial because the mass appears both on the left and on the right-hand side. Um, good. So what is a near-extremal or an extremal black hole? So if we have a solution that exactly saturates this inequality in GR, it's called extremal. Whereas if we nearly saturate this inequality, it's called near-extremal. So what is special about extremal or near-extremal black holes? Why are we talking about them today? Well, there are two facts about near-extremal black holes that are kind of interesting and unique to them. One is they become very cold close to extremality. So their temperature goes to zero. And exactly at extremality, when this inequality is satisfied, their temperature is exactly zero. The second unique aspect of near-extremal black holes is their geometry develops along ADS2 throat, which I'll explain a bit more on the next slide. Um, and it's really the physics of this ADS2 throat that's important for the large quantum corrections that I'll explain in this talk. So I said this talk was going to be about all near-extremal black holes, so all black holes that are close to saturating this inequality. But for now, we're going to restrict to just charged black holes in four-dimensional asymptotically flat space. So the theory we're going to be working with is GR coupled to the standard model fields. Um, and we're going to set the angular momentum j to zero, and I can explain what happens with angular momentum a little bit later. Um, at one point in the talk, supersymmetric black holes are also going to appear. And you're not going to need to know anything about supersymmetry or supergravity in this talk. The classical solutions in terms of the metric and gauge field are the same as the non-supersymmetric black hole. And details of supersymmetry won't be important. Um, good. So let's talk about near-extremal charged black holes. We take the inequality on the previous slide, we set the spin to zero, and we get the constraint that the mass has to be greater than or equal than the charge. Um, I've also written the temperature of near-extremal charged black holes. I've neglected the denominator here, but you can see the temperature goes to 0 as m goes to q. Okay. Below, I've written the line element, so the metric, and I've also written the gauge field. The line element is quite standard. It's nothing unusual. And because the black hole carries charge, it has an electric field everywhere outside its horizon. And that's specified by this gauge field A I have at the bottom. Okay, so on the right, I've drawn a space-time diagram of what this metric looks like. So the x-axis is the r coordinate, and the r coordinate starts on the left at the outer event horizon. So the outer event horizon is when you solve f of r outer being equal to 0. There are two solutions, but we take the larger one. And then you can increase the radius r, and the geometry looks like this. Um, there is a transverse circle here of some specified size. The size of that circle is supposed to represent the size of the S2. So the metric is some dt squared plus some dr squared piece, and then you just have a tensored on sphere given by r squared d omega squared. It might not look like it from this metric, but very close to the outer event horizon of the black hole, the size of the sphere grows very slowly. So that's represented by the size of this circle not really changing as we go along the radial coordinate. And then kind of at some large enough radial coordinate, we're far from the black hole and we get to the kind of Newtonian regime of the metric where it looks like we just have some Newtonian mass sitting at, let's say, the origin. So as the black hole goes to 0 temperature, this AdS2 cross S2 throat, where the S2 is roughly constant in size, gets very big in terms of proper distance. Its size goes to infinity as the temperature goes to 0. Okay, and then we have this kind of decoupled flat space region um, at some large enough radius. Um, good. At this point, I should make a comment. So, um, most of the astrophysical black holes in our universe have a charge to mass ratio that's very small. It's well, a standard estimate is to estimate it by the charge to mass ratio of the electron or positron, which is roughly 10 to the minus 22. The intuition people get for this is that an astrophysical black hole is in some interstellar medium with electrons and positrons floating around, and its charge can be very easily neutralized if it has excess charge by just preferentially absorbing electrons or positrons. Um, so people get this estimate by equating the gravitational force to the electrostatic repulsion for, say, an electron sitting outside the black hole. So all of the black holes in this talk are in the opposite regime, where Q over M is approximately 1. That's just a warning. Good. So like all black holes, near-extremal black holes Hawking radiate. They Hawking radiate because they have this temperature and they're able to emit low energy momentum, low angular momentum, low frequency particles. So that would be photons and gravitons in our universe. And what this kind of emission does is it decreases the mass of the black hole and drives it closer to extremality. So as it is emitting photons and gravitons, M is approaching Q. On the left-hand side, I've drawn some kind of pictorial diagram you should have in mind of this process. So some photon or some mode drawn in black is produced at the event horizon, and it tries to tunnel down this AdS2 throat and get out to asymptotic infinity. What I haven't drawn in this diagram is this photon feels an effective potential barrier by the black hole. That's not drawn, but it's some bump over here. And the photon has to tunnel through this barrier and able to escape out to infinity. And because of this barrier, lots of modes are reflected back into the black hole. So In particular, low frequency modes, modes where the frequency is approaching zero, have basically zero probability to tunnel through the barrier because to them the barrier is roughly infinitely large. This barrier tunneling probability is known as the gray body factor. Um, so if we take the gray body factor into account, we can plot the expected flux of photons we expect to see out at infinity, the photons that get passed through the barrier, and the plot is given on the right. So in the denominator here in this equation, we have the thermal factor of Hawking. In the numerator, this 4r plus omega squared is the gray body factor. It goes to zero as the frequency goes to zero. And we have an extra factor of frequency for the energy of each mode. So this plot is roughly peaked at frequencies given by the temperature of the black hole. Frequencies that are much larger are just thermally suppressed and not produced, but their gray body factor approaches 1. And in this formula, we've taken the limit of low frequency, so it's not the full gray body factor, it's an approximation for the gray body factor. Good. So what about the production of charged massive particles like the electron? Because the electron has a mass, its production, due to the thermal process, is very highly suppressed. But because the black hole has an electric charge, there's a background electric field. And we know from quantum electrodynamics that a background electric field will pair produce electron-positron pairs because of Schwinger pair production. So on the right, I've drawn a kind of illustrative picture of what happens. So if the electric field, the magnitude of the electric field is given by the charge big Q divided by the radius squared, r squared. Um, so what can happen is that a positron, maybe the dot in red, and an electron, the dot in blue, are pair produced from the vacuum in the electric field of the black hole. And then what happens is that the positron might be accelerated out to infinity by the background electric field, while the electron is accelerated towards the black hole horizon and swallowed back up. And through this kind of process, the black hole loses a little bit of charge. It loses the charge of the positron, and it loses a little bit of mass or energy. And that's measured by the energy of the particle as it reaches infinity. Now, because the particle is accelerated by the electric field, the energy of the particle is not just its mass, it's relativistic energy. So for a positron, it turns out that the kind of energy it carries away is roughly the Planck mass. It's because it's accelerated up to a ridiculous boost factor out at infinity because this throat is very long. So you can work out the dynamics and you learn that this process drives the black hole further from extremality. So you could have imagined it went either way, right? The emission of a charged particle could have brought you closer to extremality or further, and it drives you further. Good. Now, I haven't talked about the precise rate for this process. The most naive thing we could do is we could take Schwinger's formula, which he wrote down in flat space, and it's given here, and we could try to apply it to the black hole background. So this gives us a rate per unit spacetime volume. So naively, we would integrate this formula over spacetime of the black hole with the black hole metric to determine how many pairs per unit time are produced by the black hole. This would be the naive first order calculation we might try. We'll get to that in a moment on the next slide. There are two other interesting points I should mention. One is that from this formula, you can see that pairs are produced wherever pairs are largely produced wherever the electric field is largest. And because the electric field falls off with radius squared, the electric field is largest at the event horizon. So we would expect that pairs would be produced most likely close to the horizon, and then accelerated out. And further out, the pair production rate would be smaller. One other interesting point about this formula is that the event horizon radius, R plus, actually scales with the charge. So R plus is approximately big Q. So if you plug in big Q into this formula for the electric field, you can see the magnitude of the electric field actually goes down the larger the black hole is. So black holes that carry more charge have weaker electric fields outside their event horizon. This is maybe a little bit of a counterintuitive property. And this is what makes very large black holes more stable to producing charged particles. Okay, so let's try to actually integrate the formula on the previous page over all of spacetime as a first approximation. When we do that, we get this rate per unit asymptotic time at infinity in the box. The most important part about this rate is this exponential factor. So we'd like to know when this rate is very large, when the black hole is producing lots of particles, and when it's very small. And for that, we have to look at the exponent, which is set by the mass of the lightest charged particle and the charge of that corresponding particle. So if you work it out for the electron, we find there's a critical transition point. When the black hole is larger than 10 to the 5 solar masses, this rate is exponentially suppressed. And when it's smaller than 10 to the 5 solar masses, this rate is order 1. It's really large. That's telling you that when the black hole is big enough, it's producing charged particles extremely rarely, and it's very stable to losing its charge. And when it loses enough mass through standard evaporation processes below this 10 to the 5 bound, it could then all of a sudden produce many, many electron-positron pairs, and it would quickly lose its charge and become Schwarzschild-like. Okay, good. So what I told you was the standard semi-classical story for how black holes lose mass and charge. Let's get into quantum black holes now. So one of the basic assumptions in quantum gravity is that black holes are quantum systems that are really no different than heavy atoms. Of course, we don't really have a quantum theory of black holes, but we could imagine looking to atomic physics for inspiration of what we'd want such a quantum theory to do. So what are we able to do for the hydrogen atom? Well, for the hydrogen atom, we have discrete energy levels for the various states. We have discrete emission lines as the atom transitions between different states. We have angular momentum selection rules due to emission of photons. And we're also able to calculate loop corrections to energy levels, such as the Lamb shift. Ideally, we'd like a bulk theory of quantum gravity that reproduces all of the above. Maybe the surprising point is that for near-extremal charged black holes, the gravitational path integral is some kind of intermediate theory of quantum gravity that can reproduce many of the above features without giving us some complete final theory. And one other surprising thing about the gravitational path integral is it tells us that there are large quantum corrections to many observables and many dynamical processes of the black hole. So that's what this talk is about. So let me tell you what the gravitational path integral is and how we use it. So what are the rules for the gravitational path integral? Well, it's a Euclidean object where you take your Lorentzian theory, say GR coupled to the standard model, and you analytically continue it to a Euclidean theory. And what you do is you set Euclidean boundary conditions at infinity at flat space. Say you set the size of the time circle to be beta, periodicity beta, and you might set boundary conditions for the gauge field so that you fix the amount of electric charge to be big Q. And then you sum over all smooth Euclidean geometries and gauge fields on top of those geometries, and you evaluate their Euclidean action. Okay, you can do that. And then there's an interpretational step. So you've done this calculation and now you want to interpret the number this calculation gave you. The interpretational step is that this object is calculating some kind of trace over some kind of quantum gravity Hilbert space. Here it would be the trace over a Hilbert space in a sector of fixed charge big Q, and you'd weigh the states with e to the minus beta h, where h measures the energy of each of the microstates of the theory. And if you take the Lorentzian solution I presented on the second slide, and you just analytically continue it, you analytically continue the time and identify it with periodicity beta, you get the standard cigar geometry. I've kind of abused this figure. You should now think of this circle as being periodic Euclidean time, and technically the event horizon is capped off with a smooth cap to give us the standard cigar geometry. So we evaluate the action on this geometry, and what we get is this second line in this equation. This was done by Gibbons and Hawking in 77. So you get e to the minus beta m of the black hole plus the Bekenstein-Hawking entropy. So evaluating the Euclidean path integral at the saddle point level seems to be consistent with this trace over a Hilbert space interpretation. Good. But you could ask, could we do something a little bit better? So here we've just done a saddle point analysis, but can we evaluate fluctuations around the saddle point? And you can do that. And the way you practically do that is you write your metric G as this classical solution. Plus, you add on top of that classical solution quantum metric fluctuations. So you sum over modes labeled by some index n. You have some real number an, and you have some fluctuations delta gn that depends on the coordinates on top of the cigar geometry. And you do the same thing for the gauge field. You work out the action to quadratic order for these fluctuations, delta Gn. You integrate over An, and that gives you some one-loop approximation around the saddle point. So this was done by many authors maybe 15 years ago. And what these analyses showed is that if you did this, you'd basically just modify the entropy by some, well, sort of interesting factor, but it was just some overall prefactor that shifted the entropy in this formula. Um, and one thing with these past analyses is that certain metric modes were kind of missed in this expansion of fluctuations. And these modes were missed until the last few years, and they're known as Schwarzian modes. And they give very large corrections to the entropy of the black hole.
So can I ask a question?
Yes, yes.
So am I supposed to think of the action as effective action with a cutoff?
Yes, you should think about it this way. But at quadratic order in fluctuations, I guess you don't get UV divergences, so you don't have to worry about cutoffs at quadratic order.
Okay.
Can I ask a question? So, is there? I noticed if you modify the metric, if you take a perturbation and conformal factor, doesn't that lower the energy always? Isn't there? Doesn't that? So then you have a ill-defined. Unless you're in two dimensions when there's no conformal factor, but in four dimensions, doesn't that make the path integral ill-defined or?
Yes, yes. Okay, good. So strictly speaking, the path integral is ill-defined because there are some modes that just run away and are wrong sign Gaussians. And people have tried various approaches to these modes. One of the standard approaches is just to analytically continue the contour of integration for these modes to make them right sign Gaussians that make it well defined. We could discuss whether that's the right thing to do. In this talk and in yeah, what people have been doing is they've just been ignoring these modes entirely and focusing on a different set of modes.
Or maybe were people maybe thinking like in context of like JT gravity or something like this in two-dimensional systems, and then there's no conformal modes. In two dimensions, it's a well-defined situation, though. But you're not thinking about truncating to two-dimensional theory, I guess, like ADS2.
I'm thinking of the
Oh,
four
you did.
4D theory.
Okay. So then
The
you just
conform
ignore these modes then.
Yeah. The idea is that somehow there's probably a way to fix them. I don't know how. If you're fine rotating the contour, that in principle fixes them. Um, but my perspective is there should be some procedure for them, but they don't give you large temperature corrections to the entropy of the black hole, and I won't worry about them. But the
All right.
conformal factor
Thanks.
problem is a genuine problem. Yeah.
Okay, thanks.
Okay, great. Are there any other questions at this point? Okay, great. Okay, so what happens if you take into account these new Schwarzian modes? Well, if you work out their quadratic action, it looks like the following. So it looks like temperature over some energy scale. The energy scale I'll call E breakdown. And E breakdown is set by the Planck mass over the charge big Q cubed. Okay, and then there's some prefactor. The epsilon n's are basically the AN coefficients on the previous slide. The epsilon n's are integrated over to give us the one loop determinant. You can see exactly at zero temperature, these modes have zero action. So they're exact zero modes at zero temperature. And this is why they were previously missed, because in previous analyses, people studied the black hole exactly at zero temperature. But you can see at a small but finite temperature, they have a very small weight. So that makes them quite important. So what happens if we integrate over all these modes and zeta regularize to get a correction to the entropy of the black hole? What happens is you get this plot on the left. So here I've plotted the entropy of the black hole as a function of the energy E above extremality. So E is the mass minus the charge big Q. Okay, all the way to the left of the plot, the black hole is extremal, and as we go to the right, the black hole goes away from extremality. The dotted pink curve is the semi-classical answer. That's just the area of the event horizon divided by 4g Newton, and you can see at extremality, it goes to some finite large number. Good. What these Schwarzian corrections do is they make the curve the solid pink one. Instead, the number of quantum states is given by the area of the event horizon when the energy above extremality is large. But as we approach this breakdown scale, we start to get deviations, and the number of quantum states starts to decrease. And technically speaking, it decreases to 0 or 1 quantum states exactly at extremality. One other feature of these Schwarzian modes is that if you look at the metric perturbations and you plot them on the spacetime, they're very close to the Euclidean horizon of the black hole. So they're given by this blue squiggle I've drawn on the plot. So they're very deep in the ADS2 throat. Okay, good.
In the extreme, so if I'm at zero temperature, can I still see them, or do I need to take the limit?
You need to take the limit. They still exist at zero temperature. Their action is just zero. And so people neglected them in the past.
Okay. So there's no a priori way to see them just looking at zero temperature? I mean, suppose I know that they should be there. There's no way to, I don't know, identify them?
You can identify them at zero temperature. Like you can write down metric fluctuations at zero temperature that correspond to these Schwarzian fluctuations.
Okay.
The problem is they all have zero action, so how do you get some finite regulated answer from them?
Okay.
Yeah.
Thank you.
And another question, Misha. So I guess that close to the origin, this picture breaks down too, right? I mean, I mean, close to the place where rho goes to zero. You're saying there is actually one state and not. So at what scale does this break down, this approximation?
Good. Good. So what are we actually doing? We're evaluating a Euclidean partition function, right? And we're finding that as we take the temperature to zero, the Euclidean partition function is formally going to zero. So if we included literally any other contribution that was non-zero, it would become dominant over the black hole saddle we've included. So there's no hard and fast rule, but I would say that you should trust this answer while the number of quantum states is still exponentially large in big Q. So what that means is the energy can get exponentially close to extremality in big Q, but you shouldn't formally trust it exactly at E equals zero. Yeah.
I see. Thanks.
Question? Hello?
Yes.
Can I ask a question?
Yes, of course.
So, as you, in many cases that are similar to that, what one does is includes a chemical potential for the modes that are of interest, and then does the calculation in non-vanishing chemical potential, and then one can discuss limits and so on. Is that something that you've done here?
These calculations are okay. These calculations can all be done with chemical potentials as well. The short answer is yeah, the short answer is yes, these calculations can be done with chemical potentials, limits can be taken, but it's easier to think in the microcanonical ensemble where you just fix charges like big Q and energy.
The results do not change when you do it in the other way?
They slightly change, but when you convert to the microcanonical ensemble, the results are as presented on this slide. I mean, with chemical potentials, you're just summing over states with different charges, different angular momenta, et cetera, so it kind of muddles things a little bit. Good. Okay, good. Because the entropy is heavily modified, we would expect that all dynamical processes of the black hole would be heavily modified through these effects. So let's get started. This next part of the talk is going to be split into two pieces. One is neutral radiation. The summary is that you get large modifications from these effects. Then we're going to discuss the production of charged particles. There, the claim is we get small modifications due to these effects. There's a nice intuitive understanding why in the first case you get large modifications and in the second case you get small modifications. I'll explain that a little bit later. Let's get started with neutral radiation. So what do people practically do? What they do is they take this near horizon Schwarzian theory, they throw away the flat space asymptotics, and they quantize the near horizon theory just by itself. When you do that, you get a series of quantum states labeled by an energy E and a spin J. Okay? I've plotted the quantum theory on the right. So the y-axis is the energy axis, and the x-axis is the spin axis. Now, the Schwarzian theory isn't smart enough to know that the black hole has a discrete spectrum, so it gives you back a continuum of states with the density of states I've drawn at the bottom of this graph. So you should imagine that whenever you pick a point in one of these gray bars, you get a continuum quantum state with some continuum density. Exact extremality is the bottom axis down below. So a black hole with zero spin, exactly at extremality, this one state we discussed, is somewhere here. And as we just discussed, we shouldn't really trust the theory when we get down to this single state. Okay? And then the number of states grows as we go up vertically as this cinch factor. So it goes from 0 to being exponentially large when we get far above this breakdown scale. There are a few interesting things. One is that the black hole spin is quantized in this theory. So we get states at 0 spin, at h bar over 2 spin, at h bar spin, etc., etc. So from this, you can already see that we're going to get angular momentum selection rules when we have transitions between states at different spin, because this theory is smart enough to know that spin is quantized. Another interesting thing is that when you increase the spin of the black hole, the ground state energy is shifted up. It's shifted up to be this factor J times J plus 1 over 2 times the breakdown scale. So if you remember the first slide in this talk, I told you that black holes in general relativity had this complicated relationship. Extremal black holes had to satisfy this complicated relationship between their mass, charge, and spin. And this is just the quantum version of this. So when the black hole has a little bit of spin, the minimum state it can exist at is lifted a little bit. Good. What would Hawking radiation be in this picture? Well, the picture for Hawking radiation would be that we start at some excited state, say with J equals 0, and by emitting a photon, we can transition to a state with lower energy with J equals 1. How would we in principle calculate this rate? Well, we do the same thing we do, say, in atomic physics. We'd kind of write down some interaction Hamiltonian that couples the atom to quantum electrodynamics. And that would allow the atom to transition between atomic states by emitting a photon. And if we wanted to calculate the transition rate from some definite initial state to some final state, we'd use Fermi's golden rule and evaluate this matrix element here. If we started in some initial state and we didn't care what final state we wanted to go to, we'd integrate over final states. That's the second line here. Now, because we threw away the flat space asymptotics when quantizing the Schwarzian theory, the theory kind of forgot that it's coupled to the quantum fields of the standard model and can interact with them and emit radiation into them. So what we need to do is we need to recouple the Schwarzian theory to quantum fields in asymptotically flat space. I won't explain how to do this, but you basically have to study quantum fields in the black hole spacetime and study how a quantum operator at, say, Scri plus induces a source term in the near horizon Schwarzian theory through the ADS-CFT correspondence. The details aren't too important, but the final answer is that you can write down an interaction Hamiltonian like this, where curly n is some normalization constant, don't worry about it. Curly O is an operator in the Schwarzian theory, so it's an analog of a CFT operator, an ADS-CFT. And it acts on these states EI we had on the previous slide. Then we have creation annihilation operators that act on the Hilbert space of quantum fields at Scri plus. So they create modes with frequency omega or annihilate modes with frequency omega. And we integrate over all possible modes omega.
Misha, can I just, to clarify, this interaction Hamiltonian, it's essentially a gravitational calculation, an ADS2 that is done, or?
It's a calculation in the full 4D space-time geometry.
Okay.
Where you basically see how a field at infinity behaves in the ADS2 region when you solve the equations of motion. Yeah.
I see. So
There's
it's solving
a coupling, sorry, there's a
of
coupling at arbitrary high frequency to asymptotic modes. Is that what you're saying?
Sorry, say that again.
it seems from your interaction Hamiltonian that you have coupling at arbitrary high frequencies to asymptotic states. Is that correct?
Uh, uh, yes, that's true. One simplification here is that the wave equation was solved in the limit that the frequency was going to 0. So this prefactor is really in that limit and small.
So there is a cutoff somewhere hiding in this equation?
That's right. But in principle, you could couple the Schwarzian to arbitrarily high frequency modes. You just have to solve a wave equation for a mode of arbitrarily high frequency omega, and you have to solve that in the full 4D spacetime geometry and see how that couples to the theory. That's right.
And what is the physics origin of this coupling? Typically, you would expect that only low frequencies would be excited near the black hole.
Practically, it is only low frequencies that are excited because this operator O has to act on the black hole state to transition it to a lower energy state. So you can't excite arbitrarily high frequency modes.
Okay, thanks.
Yeah. But it's the same way that the hydrogen atom is in principle coupled to UV modes of the photon. Yeah.
The thing is that there is a gravitational barrier, right, between the black hole and the asymptotic modes, which cuts off most of the radiation.
It doesn't cut off high frequency modes. High frequency modes can just easily propagate through that barrier. But this prefactor is precisely the effect of that barrier at low frequency. That's how you get this prefactor.
So just to clarify, so what you need to do in order to calculate the interaction Hamiltonian is a linear calculation.
That's right.
You don't, okay. Just solving the wave equation with linear order, basically.
Yeah, that's right.
Okay.
Yeah, in the ADS2 region, there's a normalizable and non-normalizable mode of the scalar field. And you're basically just picking out the non-normalizable mode, which acts as a source. Yeah.
Okay, thanks.
Yeah. Good. Okay, so let's use this interaction Hamiltonian to calculate transition rates between states. So let's start with a simpler case of a massless scalar field. Here I've used the equations on the previous slide to calculate the energy flux. So we can imagine we start with an initial state. Energy above extremality is 100 E breakdown, and we get the following plot. So the blue is the semi-classical answer, and the orange is the exact quantum answer coming from the Schwarzian theory. We see when the black hole has a lot of energy above extremality, the two plots roughly overlap and look the same. Right. Now, if we go to an initial black hole state at very low energy, say 0.1 E breakdown, we get the plot on the right. And we see the exact quantum answer is very different than the semi-classical answer. Okay. In particular, the exact quantum answer knows the black hole can't emit modes of arbitrarily large frequency, right? If the black hole only has energy EI above extremality, it can't emit more energy than that. Otherwise, it would violate this extremality bound and create some kind of naked singularity. Okay. So the exact quantum answer forbids the emission of modes that would form naked singularities. This resolves this puzzle that was pointed out by Preskel, Schwartz, Shapir, Trivedi, and Wilczek in 91, where they noticed the blue curve would naively create tons of naked singularities for these near-extremal black holes. The quantum answer is actually not bad. I've written it here on the right. It's just some trig functions. And it has a sharp cutoff in energy. Okay. But we don't have massless scalars in the standard model, so how does the answer change for photons and gravitons? Um, well, okay. On the left, I've plotted the emission spectra for an initial black hole that's at 10 to the 5 breakdown scales with an initial angular momentum of 40 h-bar. Okay, so when you emit a photon due to angular momentum selection rules, you can either go to final states with J prime being 39, 40, or 41. And that's what I've plotted here. So these distinct curves in this plot, these lighter shaded curves, are the individual emission channels for a final black hole state with, say, 39 units of angular momentum. And you see they all differ from each other a little bit. Um, um, and the light blue curves add up to the semi-classical solid blue curve, and the light orange curves, which are difficult to see because they overlap with the light blue curves, add up to the solid orange curve. So we don't get much of a difference at very large energies above extremality. But when we go to very small energies above extremality, say EI being 6e breakdown and the initial spin being 2, we get very large differences from the semi-classical blue curve, similar to the previous slide. And unfortunately, it's hard to understand how big the differences are because I had to kind of cut off the plot because the semi-classical answer just becomes much, much larger than the full quantum answer. Okay, good. This plot also highlights one well-known feature, which is that if you start with a black hole with some amount of angular momentum, it's going to want to preferentially go to states with lower angular momenta by emitting photons. And you can see that on this plot because you end up emitting more radiation into final states with lower value of spin. So it's preferred to go to spin 39 rather than to higher spin 41, as an example. Okay, just to give you an idea of the timescales involved here, earlier I quoted this mass scale 10 to the 5 solar masses. So if you calculate the amount of time it takes for one photon to be emitted, for a black hole at these very low temperatures, you find it takes 10 to the 760 years. So these processes take a very, very long time. But one interesting fact is you can probe these large quantum corrections in an order 1 time by scattering waves off the black hole and measuring the absorption cross-section. So if we had such a black hole, we could just shine a laser at it and see very large quantum effects very quickly instead of waiting these very long times. Good.
Can I ask a question about the previous slide? Sorry.
Yeah.
So can you relate these emission rates to a thermal state with some specific temperature in both cases?
Here I've plotted things in the microcanonical ensemble. You can also do microcanonical at fixed temperature, and I have plots like that in the paper. Yeah.
Yes, but presumably the difference between microcanonical and canonical for so many states is not significant.
It becomes significant at very low temperatures because the thermal ensemble just becomes, because there are fewer states at lower energies, the actual thermal ensemble becomes dominated by states with much higher energies than you expect if you take into account these Schwarzschild corrections. So the effects become significant between the two ensembles.
Nevertheless, if I wanted to assign a temperature, for example, to the right-hand curve, what would it be what would that temperature be? I mean, if you look at the two graphs, they don't look that different.
That's a good question. I haven't thought about it. You could, in principle, fit some thermal ensemble to this orange curve on the right. I don't know the answer. Yeah, but sufficiently close to extremality, you get curves that look like this right one on the right, which is very non-thermal. So um, at sufficiently low energies, it's just not going to look anything like a thermal state. But yeah. Okay, good. So angular momentum selection rules also forbid certain transitions that are allowed at second order in perturbation theory. And a standard example is the 2s to 1s transition in the hydrogen atom, where to go from the 2s state to the 1s state, you have to emit two photons simultaneously that are entangled in a singlet state. A similar thing happens here. At small enough energies above extremality, the only states that exist have 0 units of angular momentum. And so you can't emit a single photon or a single graviton. Using standard formulas from second order perturbation theory, you can work out the transition rate for the black hole to emit these two entangled photons in a singlet state. What you find is it takes 10 to the 1450 years to emit diphotons. So when the black hole is cold enough, and it's bosonic, you stop being able to emit single photons, and the dominant transition becomes this interesting diphoton and digraviton channel. The digraviton channel is similar in magnitude. Good. Okay. I said I would also discuss supersymmetric black holes. The details of the supergravity theory aren't important. There's now some supermultiplet structure that won't play a role. The most important thing is that the plots of the spectra now look like the right-hand side. So for supersymmetric black holes, we now have a very large ground state degeneracy, which I've drawn by this thick red line. And the number of states I have labeled to be e to the s naught. So it's exponentially large. And then you have some kind of gap in the spectrum until states begin again. The gap in energy to the continuum states is slightly different than the bosonic case, but that's a minor detail. So what happens if we start in some excited state up here and we ask, what does the spectra look like for emitted scalar particles if we add, say, some hypermultiplet to the theory? Well, now the black hole can transition to different final states given by the different states in the supermultiplet. That's what all these different black arrows correspond to on the left-hand side. If you work out the final answer, you get a plot that looks like the right-hand side. So one emission channel is that black hole can transition to a BPS state. It can emit all of its excess energy into a single photon, and you get this kind of red spike on the right at one precise frequency. And then there are other emission channels when it transitions to these continuum states. So these are the various red shaded curves on the right. And all these shaded curves add up into this orange curve. So in addition to this discrete emission line that comes from emission into BPS states, we also get emission into these continuum states. So we get the sum of the orange curve and the red curve as the quantum answer. One nice thing here is that in the case of supersymmetric black holes, you can actually see discrete emission lines from gravity coming from transitions into these BPS states. This is something you couldn't see in the non-supersymmetric theory. Great. So I don't have much time left, so I'm going to give a very brief overview of charged particle emission. Okay. So what do we want to do? We want to add a charge scalar field to the theory, say the electron, and we want to quantize it on the black hole background. Now, in the near ADS2 region, the scaling dimension of the electron becomes complex because the BF bound is violated from the presence of this electric field. This was already noticed by Gubser in 2008 in a very similar context. Now, the problems with an ADS2 field with a complex scaling dimension is that probabilities are ill-defined if you want to use Fermi's golden rule. So we have to use a different formalism compared to everything I told you to calculate the emission of charged particles. What do we practically do? Well, we're going to evaluate the Euclidean path integral, where we include the functional determinant of this charged field. And this functional determinant gives us, the standard determinant of this Laplacian coupled to the gauge field minus the mass of the particle. The details of how we evaluate this determinant are not going to be important because I'm almost out of time. But the point is we want to interpret the Euclidean calculation on the left in terms of some sum over states on the right. So we're going to hope that we can write it as an integral over energies with some density of states, where we now weigh the states with e to the minus beta, a real part of an energy minus an imaginary part of an energy. So we're going to, because I know the final answer, I know that the black hole states get an imaginary shift to their energies, and when a quantum state has an imaginary shift to the energy, that tells us its decay rate, how quickly it decays. There's some Euclidean instanton calculation we can perform to evaluate this logarithmic determinant. And I won't bore you with the details, but the final answer is that at very low temperatures, we can extract the imaginary part of the energy, which gives us the rate of decay of these states. And the final answer, after we do all the calculations, you can ignore them, is this gamma. So you may not remember it, but this gamma is identically equivalent to the Schwinger rate we got by integrating Schwinger's decay rate over the entire black hole spacetime. This is just the leading order answer. There are sub-leading corrections that are just less important that I haven't included. The final conclusion is that if you do a very careful calculation involving instantons, you just reproduce the answer you would have gotten if you used Schwinger's formula. So the production of charged particles is kind of unchanged. Okay, let me quickly tell you the story of a charged black hole if we put these two facts together. So let's imagine we started with a very large black hole with greater than 10 to the 5 solar masses, so that Schwinger pair production is exponentially suppressed. What would happen is that photons and gravitons would carry away all the angular momentum, or most of the angular momentum, and carry away a lot of mass, driving the black hole closer to extremality through repeated transitions. And we jump around between states with 0, 1, 2, etc. angular momentum until we reached low enough energies that states with those values of spin no longer existed. Each of these decays takes roughly 10 to the 750 years. Eventually, only diphoton and digraviton emission will be permitted, and this takes even longer. These transitions take even more time. So the majority of the time the black hole is going to spend in its evaporation history is in this very quantum regime where Schwarzian corrections are very important. If you calculate, if you use Schwinger's decay rate, you can estimate how close the black hole is going to get to extremality. It's going to get exponentially close to extremality in the parameter big Q, but it's still going to be in a regime where the Schwarzian can be trusted because the number of quantum states is still going to be exponentially large. That's just some detail. Okay. What happens next? If you wait a really, really long time, then you emit an electron. So that's what this red curve is. We're emitting an electron, and we're jumping to a different Schwarzian theory where the charge is reduced by a factor of little q. I haven't accurately captured it on this slide, but you go very high above extremality. So the energy above extremality is much higher than demonstrated in this plot. Now we end up with a fermionic black hole. So by emitting photons and gravitons, we again decay down, but now we end up in a state with spin half. And in a state with spin half, you can emit individual photons because 1/2 tensor 1 contains half. Okay, so in a fermionic black hole state, you can emit single photons. You're not dominated by diphoton transitions. And this kind of process where you emit an electron and then emit photons and gravitons for a really long time will repeat until eventually the black hole goes below 10 to the 5 solar masses, and Schwinger pair production is no longer exponentially suppressed, and you quickly discharge by producing many pairs, and you approach a Schwarzschild-like black hole that evaporates through the standard Hawking process. Okay, good. I'm a few minutes over time, but to conclude, near-extremal black holes behave very similar to regular atoms. They have angular momentum selection rules and forbidden transitions. And the gravitational path integral tells us there are large quantum corrections to many dynamical processes of these black holes. And here I've explained how the emission of neutral particles is greatly modified, but the emission of charged particles is maybe surprisingly not very modified by these effects. If we combine all these effects together, we can get the full evaporation history of an isolated large charged black hole in our universe. So thank you.
Thank you, Misha. That was really interesting. We had quite a lot of questions, but any more questions, please? Yeah.
Can I ask? Can you hear me?
Yeah,
Yes.
I can hear you.
Okay, great. Thank you for the talk. I actually have a bunch of questions, but I'll ask just one of them. So I wanted to ask about the comment you made about exposing naked singularities. So I think you said that this process that you described prevents the emission of further particles, which is apparently to keep the geometry from exposing a bunch of naked singularities. So I'm guessing what you had in mind was a black hole that was not formed by collapse, because in collapse you don't have naked singularities in the center.
I can have an example of a black hole formed by collapse, right? So if I take a Reisner-Nordstrom black hole and I get close to extremality, and for some reason you emit a particle that violates the extremality bound, I think you would expose a naked singularity.
So I actually think you wouldn't, because first, if you have like a shell, then you don't have the singularity. The shell hides the singularity. It's very unnatural that the shell would reach the singularity because charged shells usually bounce. And then if you go to the over-extremal geometry, then the future geometry will not have trapped surfaces that will act as a mechanism to create singularities. So I'm imagining you don't expose naked singularities in that case.
Oh, really? That's interesting. Okay. I guess this is a purely GR question.
Right, exactly. It is GR.
Okay, I'd have to double check it. Maybe I'm wrong on that point. I'm not sure.
Yeah, no problem. Okay, thank you.
Right, any more questions?
Yes, let me ask one. So I'm trying to understand the difference between the neutral emission and the charge emission. And I'm thinking in terms of the Schwinger mechanism also for the neutral ones. So, and it seems that in terms of the gravitational field near your extremal black hole, it's only determined by, well, it's not that different from a slightly non-extremal black hole. And so I'm trying to figure out why is it that you get such, if you think in terms of the Schwinger mechanism, which is just pair production near the boundary of the black hole, why is it that you get this type of a large change?
Yeah, good. That's the key point. So let me go back to one figure. So I told you these Schwarzian modes were very close to the event horizon, right? So the intuition is that neutral particles are created exactly at the event horizon where these Schwarzian modes are present on the Euclidean geometry. Okay. Whereas Schwinger pair production is just a local process due to the presence of an electric field. So pairs are most
No,
likely.
I'm thinking about the gravitational Schwinger. So you have a gravitational field. Typically, what happens is that the particles are produced over a range because they are produced with some wavelengths that thermal wavelengths. And so in that case, the charge emission and the neutral emissions share a lot of similarity.
Okay. I'm not personally aware how to think about neutral emission through a Schwinger-like mechanism. The picture I have in mind is the modes are produced infinitely close to the horizon, right? And then they propagate out through the throat.
Yeah, but that's not what happens actually. And they cannot be produced in very close to the horizon because then their wavelengths would be too small.
Their wavelengths would be too
Yeah,
small.
their energy, anyhow, if you're not familiar with that, then we can have this discussion at some other time.
Right. My comment was going to be that electrons can be produced, say, on this graph over here or over here. But the point is they're produced kind of to the right of these Schwarzian fluctuations when you draw where they're localized on the geometry. So it's for that reason the Schwarzian effects don't really modify the rate
So,
the charged
yes,
particles are
with
produced
that,
by.
I completely agree.
Yeah.
I have a quick question. I don't know. Or maybe I should ask him after. Maybe you can release the people.
I think it's fine.
Uh, if I have like in the
It's fine
supersymmetric
with Misha.
setting, in a supersymmetric setting, for example, when you say extremality bound, you're talking about the ADM mass at infinity, presumably. And that can get huge contributions from things that are very far away from the horizon. For example, if you have scalar fields, the scalar fields have gradients according to the attractor mechanism, and that contributes to the extremality bound. Um, so it's the extra. I mean, the BPS condition is not m bigger than q if you have the massless scalar fields, and that's because the mass. If you imagine you have large scalar field gradients, that contributes to the ADM mass, and so you have to add that contribution to the contribution from the charge, if you like, that is roughly the energy it costs you to bring all the charges in from infinity. There's also the energy it costs you to give the scalar fields gradients to infinity. That's why the BPS band supersymmetric theory is not m bigger than q. It's m, yeah. And so, but that tells you that extremality is not something that's determined on the horizon. And so I don't see how. I was wondering how that physics of approaching extremality, how can that be sensitive to this physics far away from the horizon in your analysis? You know, the extremality band has three terms if you have master scalar fields. It's not just two terms, Q and M. It's a Q squared. The extremality is Q squared equals M squared plus another term which corresponds to the gradient energy in the scalar fields.
Yeah, from the
But that
track.
energy you need to go to infinity to measure. And so
That's right.
how can you tell if you're extremal or not just by looking at the horizon?
Yeah, good. I guess practically what you do is you start with the full 4D geometry, including the scalar fields, slightly away from extremality. Then you would dimensionally reduce on the near horizon geometry, including the profile of the scalar fields in the near horizon region. And then you would study the quantum theory quantized on that background. And you would get Schwartzian fluctuations from the standard Einstein-Hilbert action. Of course, there's other stuff coming from, say, like the hypermultiplets.
But so you're saying you want to integrate the... Okay. Yeah, I don't know. I mean, when you have the scalar field gradients, they contribute, so the mass is much less than the charge. That's the it's hard to see how to work that into an effective theory. Roughly speaking, it's because when you bring charges in from infinity, you're fighting against a repulsive force, and so it costs you energy to build. The extremality band you can understand as the energy it costs you to bring the charge in from infinity. And it costs you energy because charges repel each other. But if you have scalar fields, scalar forces are attractive, not repulsive. And so it actually lowers it doesn't cost you energy. In fact, it decreases. So in supersymmetric theories, when you have scalar field gradients, the ADM mass is actually much less than the charge because of the scalar. Yeah. Anyway, it's hard for me to see how you would how would that match your. But it is true that you can choose for specific black holes. So black holes that not like the ones you looked at, but black holes that are dionic. You can choose the scalar fields to be at exactly their attractive values and at infinity. So you can choose certain infinity boundary conditions, and then there's no scalar gradients. They just stay constant throughout spacetime, and then they contribute no energy. And then it's true that m squared is q squared, and your analysis would be true. But it's hard for me to see how it generalizes in supersymmetric cases when you have master scalar field. But yeah, that's just a question to you. I don't know if you haven't thought about it, that's fine. Yeah.
No, I didn't think about the attractor mechanism in this
Yeah. It's just that extremality is not a near horizon statement when you have scalar fields. That's what I'm trying to say.
Yeah. That's definitely true. Yeah.
So it's hard to see how to capture it in this. Yeah. I guess the other question I had, I don't know if you're aware of this. There's large black holes in de Sitter space. Then there's some paper arguing that you need something called Festina-Lente bound, which forbids forming naked singularities by emitting states. And it may be that this thing that you send these quantum corrections are somehow stop this formation. I mean, that makes a lot of sense to me. I don't think it's dynamically possible to form a naked singularity in a consistent theory starting from a state without a naked singularity. But maybe, I don't know, you might want to have a quick look at those and see if something similar could forbid forming a naked singularity in those settings. Because they argue that the only way to forbid it is by setting a certain bound on the Hubble scale. But yeah, just a comment. I don't know if there's something interesting there to understand, but yeah.
See, these are just Schwarzschild-like black holes?
No, so there's like, in de Sitter space, there's kind of two branches.
Oh,
And
these are charged black holes in de Sitter.
yeah, and large, and then in one branch, they argued that you would form a naked singularity by emission unless there was a bound relating the mass of the particles that could emit to the Hubble scale. And this way, they argued there's a certain relation between Hubble scale and the masses of charged particles. So yeah. Anyway, sorry to keep people waiting. But if you, I mean, if it's called something like Festina Lente band, I don't know. You could have a quick look at it a few minutes and then see if there's anything interesting there. But yeah, sorry. Thanks for the talk and sorry for all the long questions. Obviously, people ran away. Thanks, Shahar, for letting me. Yeah, it's a very nice talk. Thanks.
Yeah. Thanks for the questions. No, they're great. No, if
Yeah.
you could send me this paper on this bound, that would be useful. I didn't know about this.
Okay, yeah, because what you said makes sense, and it would be. I'll
Mhm.
send you something. All right, thanks.
Yeah. Thanks for